Hello again, everybody. Welcome back to Statistics. Today we're going to start our last chapter together. This is going to be section 10.1, the language of hypothesis testing. In this section, I'll show you how to write null and alternative hypotheses. We will talk about type 1 and type 2 errors, and I'll show you the difference between those. And I'll show you how to state conclusions to your hypothesis tests. Now you may notice that the one thing that's missing from this list is it doesn't say anything about actually doing a hypothesis test. That's because that's going to come in our last section in the next video, but right now we just want to get familiar with the process and with the language of hypothesis testing. I see the light at the end of the tunnel, so let's go ahead and get started on this section. Now, hypothesis testing is a very detailed, structured scientific process, but the truth is that we use a process very similar to hypothesis testing in our everyday lives. It's just that we don't put numbers with that process. So let's look at this situation from your textbook. This says, a friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If it comes up tails, your friend wins. Suppose the outcome of 5 plays of the game is 5 tails in a row. Is your friend cheating? Well, there are really only 2 possibilities here. Either your friend is not cheating and he just got lucky and the 5 tails in a row happened by chance, or your friend is cheating because he's using a coin that is not fair. In other words, he's using a coin where the probability of obtaining a tail on any one flip is more than 0.5. One of these things has to be true. Now, you can't prove either one. All you can do is weigh the probabilities. So without putting any numbers to it, you're probably already starting to compare the probability of getting 5 tails in a row to the probability that your friend is cheating. If you weigh that and you decide that the probability of getting 5 tails in a row is larger than the probability of your friend cheating, then you will believe that your friend is not cheating. On the other hand, if you decide that the probability of getting 5 tails in a row is smaller than the probability that your friend is cheating, then you will lean toward the idea that your friend actually is cheating. And that's how we typically decide things like this. We weigh the probabilities in our mind, and whichever thing seems more likely, that's what we go with. Now, I've done the math, and it turns out that the probability of getting 5 tails in a row with a fair coin is only about 3.1%, so 0.03125. Now, we know anything with less than a 5% chance of happening is considered an unusual event, so this is a pretty small probability. But suppose for a second that you believe this friend is so trustworthy that there's only a 1 in 1,000 chance that he would cheat you. If you think that the probability that your friend is cheating is only 0.001, then that probability is much smaller than the probability of getting 5 tails in a row, so you would stick with the idea that your friend has been lucky so far and he got 5 tails in a row by chance. But let's suppose that he flips the coin 10 more times, so now he's got a total of 15 tails in a row. Well, the probability of getting 15 tails in a row is 0.0000305. So now this is smaller than the probability that your friend is cheating. And so if your friend got 15 tails in a row, you would probably lean toward the idea that your friend is cheating because that now seems like the more likely event. So the point is that somewhere along the way, the probability of getting a certain number of tails will be so low that you will attribute that event to cheating instead of to chance. The process of hypothesis testing is really just finding the number here, finding the line that we have to cross before we stop attributing something to chance and start attributing it to some other cause. Let's go ahead and get a little more formal definition of hypothesis testing. Hypothesis testing is a procedure that's based on sample evidence and probability that's used to test statements regarding a characteristic of one or more populations. There are several kinds of hypothesis testing, The only one we're going to look at in detail is hypothesis tests about a mean. So we'll do that in the next section, but right now we're just going to kind of get an overview of the entire hypothesis testing process, and we will talk about the language of hypothesis testing. So the basic steps in hypothesis testing are these. First, we make a statement regarding the nature of the population, that is our hypothesis. Second, we collect evidence, that is our sample data, to test the statement. And third, we analyze the data to assess the plausibility of the statement. So even though these are not the words that we would normally use to describe how we live our lives, isn't this pretty much what we do? We have a view, we have an outlook, that's our hypothesis, and based on what we observe, in other words, that's our sample data, we weigh the probabilities and we decide what we think is true. We have to do that all the time in real life when we don't have all the information. Now, because we use sample data to test hypotheses, we can't state with 100% certainty that a hypothesis is true. We can only determine whether the sample data support the statement or not. Therefore, we never say that a hypothesis test proves that a hypothesis is true. We never use the word proves. So now let's talk in more detail about hypotheses. A hypothesis is a statement regarding a characteristic of one or more populations. We are using the word hypothesis in a way that's similar to, but not exactly like the way you learned it in science. It's not an educated guess like you might have learned in science. It is a statement about a characteristic of a population. Now, since a hypothesis can either be true or false, we always write our hypotheses in pairs. We will always have a null hypothesis and an alternative hypothesis. The null hypothesis is always labeled H subscript 0, which we say as H naught. So the null hypothesis is H naught, and this is a statement to be tested. The null hypothesis is always the statement of no change, no effect, or no difference, and it is assumed true until evidence indicates otherwise. The null hypothesis, by the way, will always contain an equal mark. So the null hypothesis is very much like a not guilty plea in a courtroom. The null hypothesis gets the benefit of the doubt. In other words, the null hypothesis is assumed true unless there is evidence to the contrary. Think about a defendant in a courtroom who pleads not guilty. He does not have to prove that he's not guilty. The court will assume he's not guilty unless evidence is provided that proves beyond a shadow of a doubt that he is guilty. In other words, the null hypothesis, like the not guilty plea, always stands unless evidence is provided that says we should reject it. Now, on the other hand, the alternative hypothesis, which is denoted by H subscript 1 and which is read as H1, is a statement that we are trying to find evidence to support. So the alternative hypothesis is H1. The alternative hypothesis is always the statement of inequality. The symbols you'll see in H1 are less than, greater than, and not equal to. So remember, the null hypothesis was like a defendant's plea of not guilty, and it always gets the benefit of the doubt. But the alternative hypothesis is like a prosecutor's allegation that a defendant is guilty. The alternative hypothesis must be supported by evidence. The null hypothesis gets the benefit of the doubt, and the alternative hypothesis must be supported by evidence, just like a plea of not guilty versus the charges in a courtroom trial. Now, I'm going to show you 3 different sets of null and alternative hypotheses, and then we are going to practice writing our own null and alternative hypotheses. So let's look at this situation first. It says there's a claim that the average number of chocolate chips in a bag of Chips Ahoy is 430. We want to find out if that number is right or wrong. So remember, the null hypothesis always contains the statement of equality, and the alternative hypothesis always contains a statement of inequality. So first, let's go ahead and write down two labels. This is H0, the null hypothesis, and this is H1, the alternative hypothesis. Now the claim is that the average number of chocolate chips in a bag of Chips Ahoy is 430. So the population mean is believed to be 430. That will be our null hypothesis. Mu equals 430. We want to find out if that number is right or wrong. We are interested in knowing if it's wrong, whether it's less or whether it's more. So the symbol we need to use is the not equal to. So the alternative hypothesis will be that mu is not equal to 430. Now, when we do the test in the next section and we draw our diagram, since we want to know about the probability that it's either less or more, we will have both tails shaded. And for that reason, this is called a two-tailed test. When the alternative hypothesis contains a not equal to, this is what the diagram looks like, and we call that a two-tailed test. You can tell because both tails are shaded. Here's the next situation. This one says the packaging on a light bulb states that the bulb will last 500 hours. A consumer advocate would like to see if the real average might be less. So again, we will have two hypotheses, always a null and an alternative. The null is the statement of equality. So the null hypothesis is going to be that the population mean lifetime of the bulbs is mu equals 500. The null hypothesis always gets the equal sign. The consumer advocate would like to see if the real average might be less, so he is contending that mu might be less than 500, so that will be the alternative hypothesis. Now, if he collects a sample of light bulbs and tests them, and he finds that the average lifetime of his sample is, say, 525 hours, well, that's not going to be evidence that supports his claim that the lifetime is less than 500, and therefore we would continue to believe that the lifetime probably is 500. For this type of test, the diagram would shade the left tail. So notice that when the alternative hypothesis contains the less than sign, which points to the left, this is going to make a left-tailed test. We would shade the left end of our diagram. So a left-tailed test has a less than sign in the alternative hypothesis. And our third situation. An old study states that the average height of women in the U.S. is 59.5 inches. A sociologist wants to find out if the average height has increased. So we will write a null hypothesis and an alternative hypothesis. The null hypothesis is the statement of equality, so the null would be that the average is 59.5. So we will write mu equals 59.5. The sociologist wants to find out if maybe the average height has increased. So he or she is interested in proving that mu is greater than 59.5. And so this would be our hypothesis pair for this situation. Now, when we draw our diagram for this situation, we would end up shading the right end of the diagram because we're interested in finding the probability that mu is greater than 59.5. And so you can see now why this is called a right-tailed test. So with the not equal to sign, that's a two-tailed test. With the less than sign, we have a left-tailed test, and with the greater than sign, we have a right-tailed test. Both the left-tailed and the right-tailed tests are sometimes referred to as one-tailed for obvious reasons. Only one tail would be shaded. Now, all three of the hypotheses that we just looked at were testing mu, but in reality, any parameter can be tested. So in this section, when you do your homework, you might see problems that talk about the proportion, which would be denoted by P, or the mean, which is of course denoted by mu, or the population standard deviation, which is sigma. Now, mean and standard deviation I know you're familiar with. Proportion we really haven't used in any problems from chapter 6 on. So let me give you an example. 10% of the population is left-handed, so the population proportion of left-handed people is 0.1. That would be a parameter, and we could do a hypothesis test to back that up. Now, we will not actually get to do any hypothesis tests ourselves with proportion. We're going to only stick with mean, but the proportion ones are out there, and so your book will throw that symbol in there sometimes. Now, let's practice finding a null and an alternative hypothesis. And when we do this, we will also state whether the test is two-tailed, left-tailed, or right-tailed. This situation says, the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experienced headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. So I think it's clear here from reading the problem that the researcher is wanting to test a proportion, because the problem doesn't say anything about mean and it does mention percent. So we are testing a proportion here. The symbol will be P. And he's interested in demonstrating that the side effect is more than 2%. So let's go ahead and label our two hypotheses. And the null always contains the equal mark. So the null hypothesis will be that P equals 0.02. Notice we don't write it in percent form, we write it in proportion form. And the alternative hypothesis will need to be that P is greater than 0.02. Now, of course, since we have the greater than symbol, it's pointing to the right. This is going to be a right-tailed test. Here's part B. The Blue Book value of a used 3-year-old Chevy Corvette is $56,130. Grant wonders if the mean price on a used 3-year-old Chevy Corvette in the Miami metropolitan area is different from $56,130. Okay, so of course we're going to have a null and an alternative. The null is always the statement of equality. Now let's see, what parameter is he testing? He wants to know if the mean price is different from 56,150. So mean is mu. So the null hypothesis will be that mu equals 56,130. And since he wants to know if the price in his area is different from 56,000, then he's interested in finding out if it's either more or less. So we just need to use a not equal sign there. So the alternative will be that mu is not equal to 56,130. When you draw it on the graph, you would need to shade both tails, and so this is a two-tailed test. And part C, the standard deviation of the contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounce. The manufacturer wants to know if a new filling machine has less variability. So, of course, this time they are testing standard deviation. The null is always the statement of equality. So the null hypothesis will be that sigma equals 0.23, and they're interested in finding out if the new machine has less variability. So the alternative will be that sigma is less than 0.23. And of course, this symbol is pointing to the left. So when you draw the diagram, you would shade the left tail, and this would be a left-tailed test. Now let's talk a little bit about type 1 and type 2 errors. You can think of the hypothesis test as putting the mean on trial. I'm going to use mu here because that's the only type of hypothesis test that we're actually going to do ourselves. So you can think of the hypothesis test as putting the mean on trial. The H naught is the plea of not guilty. Now, the researcher is like the prosecuting attorney, and the researcher is trying to find evidence that H naught is false. So, if the researcher cannot produce any evidence that mu has changed, then H naught stands. Of course, mistakes are possible. Just as people can be wrongly convicted of a crime and guilty people can be wrongly acquitted, it's also possible for the results of a hypothesis test to be wrong because we're dealing with samples and probabilities, so we never know for sure. Now, there are 4 ways a hypothesis test can come out. In reality, either H naught is true or H1 is true. They can't both be true, but one of them has to be true. Now, when we do our test, we will either reject H0 because we believe it's false, or we will not reject H0 because we don't believe it's false. Now, if we reject the null hypothesis when the null hypothesis is false, then that's the right thing to do. So that's a correct decision. If we fail to reject the null hypothesis when the null hypothesis is true, that's also correct. So if H0 is true and we do not reject H0, that would be a good decision. But if we reject the null hypothesis, that is, if we believe the null is false when it's actually true, that's called a type 1 error. Type 1 error is when the null is true, but we reject it because we've decided it's false. That is a type 1 error. And then the fourth thing can happen is that we do not reject the null hypothesis, but actually the alternative is true. So we believe the null is true, but in reality the alternative hypothesis is true. That's called a type 2 error. Now, it's so easy to get these confused because these are just arbitrary names. You just really have to think about both situations and memorize it and get it in your head that a type 1 error is when we reject the null hypothesis although it's true, and a type 2 error is when we fail to reject the null hypothesis although in reality it's false. One thing that helped me when I was learning this is to compare it to a courtroom trial. So remember, the mean is on trial, and H0 is the plea of not guilty, and H1 is the prosecutor's allegation that the defendant is guilty. So, if we reject the null hypothesis when the null hypothesis is false, that's like saying we've decided that the not guilty plea is wrong, and in fact the not guilty plea is false. And so that's like convicting a guilty person, and that's a good thing. Also, not rejecting the null hypothesis when the null hypothesis is actually true, that's like acquitting an innocent person. So remember, the null hypothesis is the not guilty plea. So if we don't reject the not guilty plea, in other words, we believe the not guilty plea is true, and in fact it is true, that's like acquitting an innocent person. That's a good decision. Both of these are right. But a type 1 error would be when we reject the null hypothesis although the null is actually true. That's like convicting an innocent person. That's a mistake. So that's a type 1 error, convicting an innocent person. And a type 2 error is failing to reject the null hypothesis when the null hypothesis is false. That's the equivalent of acquitting a guilty person. So that's like at the end of the trial, we still believe the not guilty plea, but in fact the not guilty plea was a lie. That's a type 2 error. So let's go back to the Medco Pharmaceutical Company and let's look at this situation. The Medco Pharmaceutical Company has just developed a new antibiotic. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience a headache as a side effect is more than 2%. The researcher conducts a hypothesis test where the null hypothesis is p equals 0.02 and the alternative hypothesis is p is greater than 0.02. What would it mean to make a type 1 or a type 2 error? Okay, remember, type 1 error is when we reject the null hypothesis even though it's actually true. So in a type 1 error, the null hypothesis is true, but we reject it because we believe it's false. So in this case, a type 1 error would be to conclude that the proportion of children who get headaches as a side effect is greater than 2%, when in fact it's not. See, if we reject the null hypothesis, that means we've decided that the alternative is true. And then a type 2 error would be that H0 is actually false, but we fail to reject it. So in a type 2 error, we would conclude that the proportion equals 0.02 when in fact it's greater than that. Now recall from Chapter 9 that we never know for sure whether a confidence interval contains an unknown parameter. We only know the likelihood that a confidence interval captures the parameter. That's why we would always say we are 95% confident or we are 90% confident. We know the likelihood that the confidence interval captures the parameter. Well, similarly, we never know for sure whether a hypothesis test is correct or not. So, just like we put a level of confidence on a confidence interval, we also can determine the probability of making an error on a hypothesis test. Do you remember alpha from chapter 9 when we did confidence intervals? Remember alpha was the area in the tails? Well, alpha, it turns out, is the probability of making a type 1 error. That is, alpha is the probability of rejecting the null hypothesis when the null hypothesis is actually true. And then beta is the probability of making a type 2 error. That is, beta is the probability of failing to reject H0 when H0 is actually false. Now, we can't directly control beta, but we can control alpha. So the probability of making a type 1 error, that is alpha, is chosen by the researcher before the data is collected. Alpha is referred to as the level of significance. The level of significance is the probability, again, of making a type 1 error. The choice of alpha depends on the consequences of making a type 1 error. If the consequences of making a type 1 error are severe, then the level of significance should be small. That is, we want to minimize the probability of making a type 1 error if the consequences of making a type 1 error could cost someone their life, for example. On the other hand, if the consequences of making a type 1 error are not severe, then a higher level of significance can be chosen. Like we might let alpha equal 0.05 or 0.1. So I know what you're thinking. You're thinking, well, why not always just leave alpha at 0.01 then? Well, that's because alpha and beta are related. If we make alpha small, that means we're making beta larger. So we also have to take into account the consequences of making a type 2 error. For example, the laws of our justice system are supposed to be set up to minimize wrongful convictions, but that means by definition that more wrongful acquittals are possible too. Does that make sense? If we fix it where it's hard to convict innocent people, that means by definition it's harder to convict guilty people as well, so every now and then a guilty person's going to go free. But we've decided in this country that we would rather have it that way than the other way. There's no way to minimize the probability of wrongful convictions and at the same time minimize the probability of wrongful acquittals. We just have to decide which type of error we think is more important to avoid and minimize that probability with the understanding that the other one is going to go up to some degree. Okay, so much for type 1 and type 2 errors. The results have to be stated. Notice now that we never accept the null hypothesis. We never say that we've proved the null hypothesis is true. We can't prove the null hypothesis is true, just as a defense attorney never tries to prove that his client is innocent. You let the prosecutor prove that he's guilty, but nobody ever proves that the defendant is innocent. It's just that if we can't prove he's guilty, we have to assume he's not guilty. Now, notice that we never accept the null hypothesis. You can't prove that the null hypothesis is true. Similarly, no defendant on trial is ever declared innocent. They only can be declared not guilty. In other words, if the jury finds someone not guilty, that means that there was not enough evidence for the jury to reject the defendant's plea of not guilty. So the jury never comes back and says, we believe this person is innocent. They only can ever come back and say, we believe that the prosecutor didn't prove this person is guilty. Do you see the difference? It's an important difference. Because we can't prove these hypotheses, we only can say this one is more likely or that one is more likely. So in hypothesis testing, the way we talk is this. If we've decided that the null hypothesis is false, we say that we reject the null hypothesis. If we can't prove that the null hypothesis is false, we only say that we fail to reject the null hypothesis. Notice again, we don't say that we reject it or we prove it. We say that we reject it or we fail to reject it. So this is like a jury coming back and saying, we convict this person, we reject his plea of not guilty, or we acquit this person, we fail to reject his plea of not guilty. Again, we never say that we've proved H0 is true. Okay, now let's go back to the Medco Pharmaceutical Company and let's look at this one more time. Same hypothesis test, I won't read it to you again, but suppose the sample evidence indicates that the null hypothesis is rejected. We want to state the conclusion. Okay, the null is rejected. That means we've decided that this is false, and therefore we believe this is true. That means we're going to say there is sufficient evidence to conclude that more than 2% of children experience headache as a side effect. So remember, if we have rejected the null hypothesis, it's because we had evidence. Just like in a trial, if somebody gets convicted, it's because the jury believed the evidence against them. So when we reject the null, there is sufficient evidence to conclude that this is true. On the other hand, let's look at part B. Suppose that the null is not rejected. Okay, so if the null is not rejected, that means that we still believe the null is true, or at least we don't have any reason to believe it's not true. So this time we are going to say there is not sufficient evidence to support the claim that more than 2% of children experience headache as a side effect. So notice that in both answers, we started by saying there is sufficient evidence or there is not sufficient evidence. If the null is rejected, it's because there is sufficient evidence to do so. If the null is not rejected, it's because there is not sufficient evidence to do so. Then notice that after we say whether there was evidence or not, we state the rest of it in terms of H1. Let me flip back. When the null was rejected, we said there is sufficient evidence to conclude that this alternative hypothesis is true. But when the null is not rejected, we say there is not sufficient evidence to support the idea that this alternative hypothesis is true. And so that's it. And I think the most important thing you can get in your head right now is that the null can only be rejected because there is evidence to do so. If the null is not rejected, that means there was not sufficient evidence. Otherwise, the rest of these words can vary. I don't want you to be too concerned about that, but I do think it's very important that you know whether you should say that there is sufficient evidence or there's not sufficient evidence. And the rest of it we can worry about later.